Hi, my name is Raman. So I've been working this semester so far on like Raman spectroscopy. I've been taking all the greases that we have and trying to find Raman spectra in a way that we can identify them. So yeah, okay. So typically I'm going to categorize them as having spectra or being fluorescent. So I'm going to start with the ones that did have spectra. This is just a list of all the oils. The vegetable oil through the Dow Corning 3 are all solid greases. I have asterisks by them because I had issues. I initially put them on a microscope slide, and after like getting the blank spectra of that, that spectra showed up in like all of the solid greases. So then I started experimenting with different types of backgrounds. I did aluminum foil, same problem. I did anodized aluminum. I think that was pretty much the same problem. So I've also been trying to look into if there is silica in these greases, because that would explain why the frosted glass spectrum is showing up, because it is a silica-based microscope slide.
Yeah.
And then the bottom 5 are all liquid greases. In this case, they all did actually have independent spectra, which is quite nice, because I used a vial, like a glass vial instead of a slide. The only problem I did run into with like the Biz 2-ethylhexyl and the canola oil is that I couldn't get the base down to be flat. And like I would change the integration time, and I would take like 2 or 3 dark spectra to blanket just to make sure, and then every single time it wouldn't be on the baseline. Like there'd be peaks, but it wouldn't be on the baseline. I put that in the Word document, the 3 that were giving me issues.
Excellent.
And then there was one. So this is just an example of one of the spectra. I didn't put all of them in, but this one had unique peaks. So.
Yeah, I think that's a silicon-based oil. You don't see any CH stretches. It's all, if there's any H's in there, they're bonded to silicon. So.
Well, at least I don't have frosted glass in there.
Exactly.
I'm happy with that.
Kidding.
So.
Yeah, look at that.
Okay. This next slide, I have all the ones that fluoresced.
Oh, nice.
Yeah, so this is just a list of all the solids and all the liquids. So I think like the majority of the liquid greases were fluorescent. Typically all the ones that had color to them were fluorescent. And this is what the spectra looks like. If it's fluorescent, it's the same for all of them.
Yeah, and so can you give me an idea what the maximum signal is up there?
I think it was around 180,000 or 200,000.
Yeah, 180 to 200,000 counts. And on a baseline of like 300, so signal to noise is huge. Yeah. And your integration time?
Typically I kept it at 1,000.
Yeah, which is 1 second, which may be kind of high, but.
Yeah.
But
well, it didn't really. I mean, if I noticed if I changed, and like especially with the solid greases, when I would change the integration time to be like 300 or 400, instead of being like a square, it would be like an oval, like kind of rounded top. But it would still be saturated.
Because this is saturating the detector completely. Those you're at least collecting the signal.
It's still like.
I think the lowest integration time I was able to use on this Ocean Optics detector was 15 milliseconds. So 0.015 is about as low as I've gone.
I kind of capped it at 200, and I was like, I'm not really getting anything off of this.
Yeah, so you can always go lower until it won't go any lower. Until you're taking the spectra as fast as you can, and just looking for those sharp peaks. But we didn't. I looked with you. We didn't see any sharp peaks. But that's a good thing to see fluorescence in these contaminants, because fluorescence is so sensitive. So we'll be able to track the residues pretty easily using fluorescence. Yeah.
Why does it? I mean, I can't really see it, but why does it start so far below 0?
Yeah, I don't exactly know, except that it's it looks like it's been normalized to some degree. And so that's a question I have as well.
Okay.
I don't exactly know why it's going from negative 80,000.
Did it on all of them.
Yeah, so it's probably just because it is so saturated
with
the detector, but I don't know why that would push that signal down.
I did notice I didn't put the trim C350 up on here, but I want to say that was like half fluorescent.
Okay.
Because there were like peaks, but it was like way like above the baseline.
Huge baseline.
Yeah, and when I used an LED flashlight on all of them to kind of test, and that one was like half glowing, half not glowing. But I threw it under the fluorescent.
Yeah. And
Because
so
you could-
again, the fluorescent molecules may not be the greases; they may be some additives, you know. And so if they're putting some antioxidant in there that's fluorescent, it might have less than the others.
Yeah.
Okay.
And so, to kind of further explore the fluorescent greases, I took the solid greases, and I like smeared them between two microscope slides, and then I used a fluorimeter to kind of get like the fluorescence, the emission and excitation wavelengths to see if that was a way that we could like quantify or like
Sure.
isolate the fluorescent greases. So here I have an example of like the first read. I took a 3D scan, and that just kind of gives me where the peaks are, so that
Mhm.
where I have the cross section, it's kind of like a little,
Yeah.
I guess, hill you could say, and
Right.
that's where you have to isolate. That's where your excitation and your emission wavelengths are going to be.
Okay, so let me just go to the axes. The vertical axis is the excitation wavelength. So that's the monochromator letting the source in. Yeah. And then the x-axis is the emission wavelength. Just for the video.
Oh, yes,
Yeah.
yes, those are the.
And so then we're sitting right on that little shoulder. Yeah. Okay.
So there was a problem. I did normally, or baseline, it's about 700 volts. I had to lower it to 400 volts because that white area in the middle, it's called flat topping. That's when your signal is too like fluorescent.
Yeah.
And so these were the excitation and the emission wavelengths that I got for the 3 solid greases. So the AP-azon was the one that was like most distinct because it was at 326 compared to 350. I discussed with one of the other professors in our department, Dr. Thompson, and he said because the white lithium and the marine grade are pretty much the same excitation wavelengths, that could just mean that they have like the same additive that fluoresces, and so like in the future I could like maybe like if I wanted to quantify it, they might have the same type of additive, but they might be in different amounts, so that could also be a way to differentiate. But I
Never
haven't,
got it. Yeah.
yeah,
Well, that's
haven't
good.
gone that far yet.
Okay.
That's all I have.
All right. Fantastic. I think it's good to have fluorescent soils just because you can track it with a black light if it's strongly contaminated, and then the laser is so sensitive. I mean, if there's just a small amount on there, like you said, you smeared this on a microscope slide, so you know a thin film is enough to saturate the detector. So, you know, presumably you could get pretty close to a monolayer of contamination and still see fluorescence with some laser systems. You know. I don't know if ours is going to be that sensitive, but it would definitely be much less than a thin film we could see. So that's good to know. Next, I want to mix in the rubber cement. I want to mix in some fluorescent powder instead of the carbon black, and so we could turn it. And the rubber cement itself fluoresces, doesn't it?
It does.
We noticed that as well. So, I mean, maybe we don't even need to do the fluorescent powder, but I think visually with your eye, you can see that fluorescent powder so much easier, even just with the room lights. So for our cleaning demonstrations, you know, if we goop up the threads with fluorescent pink powder, you know, laced soils, and run that through the ultrasound, I mean, you can look at the threads and see how clean they are. You don't need an instrument. You know, your eye is good enough detector for that. Using carbon black, you should be able to still see it, but with shadows, you know, is it still dirty or is it just the shadow? When you put pink powder in that groove, you're going to be able to see that. And so I think that'll be the next thing, is to try to look at the rubber cement formulation with pink fluorescent fingerprint powder, and that polymer should disperse it, and then we'll be able to track it. So I think we're on our way to making some really good demonstrations.